Let's take a look at an example problem for Module 11.2 for ME 270 Structural Dynamics. So in this example problem, what we're going to do is take a look at a three-story shear frame building. Now for this problem, they tell us that this building shown down below in this figure here, so here's our figure down below for the shear frame building with 3 stories. They want us to determine the free vibration response given the following initial conditions. So they give us the initial conditions that x of 0 is equal to, we have this vector right here of 1, 2, 3 in units of inches, and x dot of 0, this initial condition here, is equal to negative 1, 3, and 4 in units of inches per second. Now they also give us our k values and our m values. You can see we have mass 1, mass 2, and mass 3 here, and we have k1, k2, and k3 on either side of the building here, by the frame. So our K values, or K1 is given to us in units of kips per inch, and it's 25.9, K2 is 111.88, and K3 is 174.82. They also tell us that our M1 is equal to 0.5823, our M2 is equal to 0.04658, and M3 is equal to 0.03494. So with all this information here, we can relate it back down to where those variables fall on our diagram for our three-story shear frame building. So now that we've had a chance to read through the problem statement, the next thing that we want to do is take that information and create our setup page. So we have an example problem here. We're told that we have a three-story shear frame building here, and we have our initial conditions given here, x of 0 and x dot of 0. We redraw out our diagram over here. We put in our given values of K1, K2, K3, M1, M2, and M3, and we know that we're looking for our free vibration response is what they ask us to solve for. So now I have a page that I can reference back to. I can see my initial diagram, I can see my initial conditions, and I can see all of my given values for my spring constants and the masses associated with that diagram. So now that we have that information, we can reference back to those pages. The first step here at the beginning of our solution is to talk about our mass matrix here. So our mass matrix is given by this vector, or this matrix right here. So M is equal to, and now we see here we have M1, M2, and M3 going down the diagonal right there like that. And we can plug in our known values to this mass matrix here. So we're given our M1, our M2, and our M3, and we can plug that in. M1 is 0.05823. M2 is given to us as 0.3658, and M3 is given to us as 0.03494. So now we'll create our stiffness matrix in the same manner that we created our mass matrix there. So our stiffness matrix K related back to our three-story shear frame building over here. We have our K1 over 2, K2 over 2, K3 over 2 related to the two sides. At each of those locations there in between our three masses, M1, M2, and M3, that are all rigid. So our stiffness matrix takes the form here of K1 plus K2, negative K2, 0, negative K2, K2 plus K3, negative K3, 0, negative K3, K3. Well, we have values for K1 and K2 and K3 given to us in our problem statement, so we can take these values now and plug in. K1's everywhere we see a K1, K2's everywhere we see a K2, and our K3's everywhere we see our K3's now. So we do that there, and when we plug in our known values, we end up with this relationship down here that our stiffness matrix K with our numeric values plugged in is 137.78, negative 111.88, 0, negative 111.88, 286.7, negative 174.82, 0, negative 174.82, and 174.82 there in units of kips per inch. So next step is to talk about our equation of motion. We have our general formula here for our equation of motion of mx double dot plus kx is equal to 0, where we know we have our mass matrix here, our 0.05823, 0.04658 for our M2, and for our M3 we have 0.03494. So those are plugged into our mass matrix M here. And we have our spring stiffness matrix over here, our K value here, 137.78, negative 111.88, 0, negative 111.88, 286.7, negative 174.82, 0, negative 174.82, and 174.82. We've calculated before, so we've got our M matrix and our K matrix that can plug in here for our M and our K into our equation of motion there, and we have our initial conditions here as well, so we can plug that in for our M matrix right there, times our X double dot plus our K times our X values here are equal to 0. So as we continue on with our solution to this problem here, the next thing that asked us to solve for was our omega 1, omega 2, and omega 3. So what we can do is we can go to equation 10.5 in our textbook, and we can see that we have the determinant here of our K matrix minus omega squared times our N matrix is equal to 0. So what we can do then is plug into this here. We can say, okay, we know our K matrix. We have numeric values for this here that we've already solved for. And here's our M matrix right here. So then we take this omega squared, multiply it through our M matrix here, and we have each of these with an omega squared term next to them. And then we can say K minus, so 137.78 minus omega squared times our 0.05823. So there we have that there. Then we have here this value minus 0. That carries over. 0 minus 0 is a 0 there. Then we have a negative 111.88 minus 0 is negative 111.88. We have 286.7 minus our 0.4658. Here, we end up with this relationship here because we have an omega squared multiplied through that as well. So there's this right here. Then we have a negative 174.82 minus our 0 term there is negative 174.82. And now we go down to the bottom row and we say 0 minus 0 is 0. And we say negative 174.82 minus 0 is negative 174.82. And now lastly we say negative 174.82 minus omega squared times our 0.03 there is this right here. So now we come up with this matrix here. So now what we can do is we can take the determinant of this matrix here and solve it for omega 1, omega 2, and omega 3. Now you could go through and do this by hand. You could plug it into Excel. You could plug it into MATLAB. And what you end up with here is your omega 1 is equal to 13.02 radians per second. Omega 2 is 55.3 radians per second, and we have our omega 3 here of 101.44 radians per second. So the next step in our solution is to solve for our mode shape. We get our general equation for our mode shape given by this here, and we look at this, we realize that we're also going to need our dynamic matrix because we have this d right there of omega r for both of these. So we recall back our dynamic matrix is given by this equation right here. D of omega r is equal to our spring constant, our K matrix, minus omega r squared times our M matrix. So that's this matrix right here. So we have that there. We already have our numeric values for it. And then what we need to do is get our DBB and our DBA. So we can see DBB, DBA that we need to get out of this. Well, how that corresponds is our DAA right here corresponds with this portion of our matrix right here from our dynamic matrix. Our DBA corresponds with this guy right here. And our DAB corresponds with this right here. And our DBB right here corresponds with these terms right there. So those are how we get that from our dynamic matrix right there. So our DBB, when we plug into that there, we can see, okay, that is these four terms down, this, 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 and this. So there's our matrix right there, our 2x2 matrix for our DBB. Our DBA, we go up here, okay, that's this right here, which is this guy right here. So there we got our negative 111.88 and 0. And we can plug this value right here back up into our mode shape equation up top here. So there's our DBA right there that we can plug back up into that there, and our DBB can go right into this right here. So when we do that through, we plug those in, we solve that, we take the inverse of our DBB, multiply it by our DBA right there. What we end up with is our mode shape for theta of B here is equal to a 1.143 and 1.183 right there. So now this was just for our omega 1 term right there. We can continue this on and repeat the same for our omega 2 and our omega 3 terms, where we have values for omega 2 of 55.36 radians per second and omega 3 of 101.4 radians per second. So therefore, when we plug everything in, what we end up with here is our mode shape of 1, 1, 1, 1.143, negative 0.364, negative 4.118, 1.183, negative 0.94, and 3.897 when we do this out for all three of our omega terms.